This is getting scarier every time I see it.
Don't kick it.
Does someone have a portable 2.4 kilovolt generator?
Yes. Yeah, I got one in my pants.
It's one of those things you instantly regret saying when that happens. So why are you guys all in suits? What's the story? And more to the point, why are you guys not in suits? This side is showing you up. I expect everyone to dress respectfully, and that means suits. Oh, well done, guys. Where's my suit? I left it at the cleaners. Okay, now, I've been thinking long... Put the camera away. I've been thinking long and hard about the dilemma that... this weird dilemma I seem to be encountering, which is looking over everyone's task 1 diaries, I'm seeing generally fantastic work. I'm seeing people who are having brilliant ideas, lots of people who are getting it all out, or certainly most people are really well on the right track and have had really good ideas. So there's this sense, as I look over that I think, wow, the course is great. But then we have this other dilemma that there seems to be this gap in programming. And maybe, I've been chatting with the tutors about it all the time, it's on our minds a lot. Maybe it's just a perceived gap, maybe you've just lost confidence or something after first semester or something. Not sure what it is. Anyway, today I've decided it's coding day. I'm going to do nothing but code. So we're just coding. So, if you are having problems coding, I'm slowly putting up some resources you can use to help teach yourself. But can I emphasize the point from last lecture that I might not have made clearly enough? Because some of the tutors were sitting in the room and afterwards they said, they were commenting on the fact that everyone's idea for how to improve programming was us doing all this extra stuff to help you improve your programming. And of course we're more than happy to do that. There's no problem with us doing that. But at the end of the day, the only way, I said it, but let me say it again, the only way you're going to learn how to improve your programming is to do it. Yeah, you just got to do it. There's just no alternative. You can listen to us talk about it forever, and it won't improve your programming that much unless you actually do programming. So I encourage everyone that's having the least bit of problems or nervousness or anything just to sit down and practice and do some simple examples. And I suggest do a couple of hours practice a day. Every night before you go to bed, do an hour or 20 minutes or however long you can spare. Get up 20 minutes earlier and do 20 minutes. Just do it over and over again for a short period of time until you get back in the groove of being confident. I don't think most people have much to go. Most people seem to understand algorithms and pseudocode and C. The problem seems to be with malloc, pointers, arrays and strings, which is, a typical sticking point in C. Okay, the last course was where that was to be conquered, but it's not weird that you're having problems with that because everyone has problems with that. So I'll put some more resources up, and I made some videos last year about that actually. I'll put them up too just so you can look at those. And we'll do everything we can, but at the end of the day, don't forget, the ball is in your court. If you want to master this course, you really do need to be able to program, and you need to be confident with your programming. So put a week or two into just working your butts off until you have regained that confidence. And I don't think it's hard. You haven't got much to go. Just looking at all the quality of the work, I'm seeing lots of good stuff. Most people now are doing 2 lab questions. For a while, everyone was just doing 1. But most people this week have been doing 2. That's fantastic, because that's how many you should be doing. Don't forget to start your labs in advance. Don't leave them to the last minute. As of next week, we're going to start having the labs submitted electronically on the Monday. So this is going to free up, this is part of our plan to sort of help you program. This will free up your lab time. So instead of the lab time being a long marking time where the tutor can't help you, the lab time now will be a time where the tutor has 2 hours to walk around and help you. And marking will only take a split second because it will have been done automatically before you turn up to the lab. So again, just to try and help you. So start the labs early, work on them hard, do lots of practice, work hard. And at the end of the day, you're going to feel so tired. Good. Okay, now let's return to the subject for today, which is just continuing with this theme. Remember, we were recapping on science. Blah, blah, blah. We looked at habits of a scientist, which is assignments testing. Then we looked at skepticism, and we got stuck on skepticism. We're still talking about skepticism. And today, in fact, we're starting with skepticism. And the point still to be covered today is the third point, which is abstraction classification. So let's start with skepticism. The take-home lesson from yesterday was if you're writing a program and you're writing a program, who's the best person to test your program? You. Who's the worst person to test your program? Yourself. Because we just see what we want to see, believe what we want to see, and we don't want to say that again. We don't want to. Yeah, that's what beta testing's about. You think your program's right, so you put it out and everyone shows you how wrong you are. The best people to find mistakes in what you've done are other people because they believe they're there. Deep down, you don't believe they're there, so you don't look hard enough. And we looked at examples from science and so on and so on and so on and so on. All right, so it turns out, and this is something that I think computing students always find a bit weird, that although the hardest thing initially might seem to be mastering syntax and pointers and structs and getting C to compile and not getting seg faults and things like that, actually it just takes a while and then you get it. It's like playing the flute. It takes a while to hold your mouth in the right position and just remember where the notes are on the flute, and for a long time you think that's the hardest part. But once you can do it, is there anyone here who plays the flute? The electric guitar is very similar to the flute. I reckon you could make the strings resonate by blowing on them and touch points on it. Yeah. I'm sure. But is there anyone that plays some sort of wind instrument? Yes. What do you play? Sax. Cool. What sort? Whoa. Sorry. See. Well, I knew that was going to happen. It's either the computer or me that's going to die, or both of us. I guess. Yeah. I'll just put that back. But we all know what's going to happen. Alto sax. All right. So, do you agree when you start playing the sax? I used to play the sax. I sounded like a car horn, and it used to really depress me. I practiced for about a year and I still sounded like a car horn, and I didn't sound like, some awesome sax player. And all I could think about was how hard it was to actually get the keys in the right spot, to actually make a sound, to hold your mouth, to get that embouchure, to do all that sort of stuff. That's all I could think of, and that's what I thought sax playing was all about. But once I could do that, and presumably you can do that. Yeah. Do you realise you don't really think about that anymore, do you? What do you spend all your time worrying about now? Making it sound good. That's the real problem with the sax. It's the same with programming. I just have to censor some things in this lecture. I hope that's okay. That's the same thing with programming. At first you're going to think malloc and all that stuff's the hardest thing because it's the problem right in your face. Did you just plug something in too? Oh my God, it'll be like the end of the lecture and I'll be just... that tasted delicious. Currants. So you get the point. I'm labouring the point, but you get the idea. So don't think that the hardest thing is programming. You will soon be past that, and the real hard thing that will await you, what joy, I'm telling you, as you pass this problem, there's another one lying ahead. The real hard problem facing you is just writing programs at work. It's really hard to do. You can eventually write simple ones at work, and the better and better you get, you'll write more and more complex ones at work. But no matter how good you are and how smart you are and how many years you've been programming, it's impossible to write a program that's non-trivial that actually works. Yeah, seg faults, whatever. There's always going to be problems. Every programmer gets them. There's not a programmer in the world who would, if they were in this room now, wouldn't be nodding sagely and wisely. No matter how good you get, you never get to that point where you can do things without making mistakes. In fact, the mistakes grow. Well, let me tell you how the mistakes grow. Mistakes arise when complexity exceeds our ability to spot it and fix it at the keyboard. Let's have a look. Murphy's Law. Yeah, Murphy's Law. We're looking at the maths of Murphy's Law. If you've got a program and it's got three concepts in it, three things in the program, maybe they're three variables, maybe they're three functions, three aspects, and these things all interact with each other. How many interactions do you have to worry about to check the program's right in your head? Oh, I've got to check that this combination of things doesn't kill me. And how many combinations do I get? Yeah, this guy might interfere with him, so I better check that doesn't happen. And this guy, when it happens, it might stuff up this thing, this invariant, this line of code, this variable value, whatever it is. Oh, okay. And so how many different ways are there of finding pairs amongst three things? It's not 3 factorial. Well, it's 3C2. Which is equals, does anyone remember the formula for 3C2? NC2, I might write it more generally. NC2 equals n times n minus 1 over 2. There's that formula again. The number of interactions is given by this formula. So if I have 5 things, suddenly, whoa, I can handle that. I'm a super elite programmer. But now I've got a program with 5 things, 5 functions, 5 global variables, 5 whatevers. And now whenever I fool around with one of them, I've got to check that I don't break the other things, because that's what's going to happen. So I've got to worry about the way that can interfere with that, and that can affect with that, and that can... And how many am I going to draw eventually? If I just draw all this, it's going to look like an evil diagram, isn't it? But how many is it going to be at the end? I won't finish it. Will someone, he who can't be named? Voldemort, of course, I'm talking about. Okay, Voldemort, whose name's backwards, is I can't believe it's not fiction. So there are how many? 5C2, which is growing. How's this growing? If I was going to plot, 3 had how many interactions? 3, and 4 had how many interactions? We didn't work it out, and 5 had 10 interactions. And if I kept plotting this and I drew a picture of the number of the size of n down this column versus the number of interactions on this column, what sort of picture am I going to draw? Quadratic. It's going to be a quadratic. Yeah. It turns out, and I think this is a problem that all problems have, a characteristic of all problems, that as things get bigger and more complex, the number of interacting components increases quadratically. So the complexity grows very rapidly. And actually, as a problem gets slightly more complex in size, let me say that differently. As a problem gets slightly larger in size, it gets massively more complex. And this is probably what you've noticed. You can do trivial programs, and then once we ask you to write something that's slightly harder than trivial for the lab, instead of taking 1 minute, it takes half an hour. And if we make something that just seems even just slightly harder than that, suddenly it takes 2 hours. And we give you an assignment that, looking at it, doesn't really look all that much. When you look at the number of lines of code at the end, it's maybe going to be twice as long as your longest lab. But does it take twice as long as your longest lab? No way. It takes 4 times as long as your longest lab. The complexity in computing grows at least quadratically. So the secret that we try to keep away from you programmers when you're starting to learn is the real problem in programming is dealing with all the errors. Your brain doesn't grow, your brain, however big it is, I've got this size brain, you've got that size brain, some guy's got that size brain, doesn't matter how big it is, you just have to increase it a bit more and the complexity exceeds it. So no matter what software you're writing, it's riddled with errors. Software is wrong, errors, crap. That's for the exam, don't forget that. So yeah. In fact, a programmer once told me this really funny thing that I've never forgotten, which is, he said, why do you think we call bugs, bugs? And, I parroted off all that lame stuff about, when they set up ENIAC and Ant crawled into one of the Mercury delay, or some rubbish I read somewhere. And he just laughed and said, no way, that's not why we call them bugs. The reason we call bugs bugs is it sounds friendly and innocuous. And no human being that was a programmer could put up with the mental shock of having that many errors, that many mistakes. So you say, my program had a few bugs, not my program was wrong. It was stuffed. It was full of errors. So when someone says, how did you go today? Oh, good. I wrote some programs, but they were all wrong. You can't say that. You say, I wrote some problems, there are a few bugs. It just sounds much... It's just how we try and deal with the psychological impact of the fact that everything we do is wrong. So really the hard thing when you're writing programs is managing this getting it wrong. And it's the same in science. If you were doing science and trying to investigate something about the outer space or the universe or something like that, it'd be easy to get the wrong measurement or not have the right telescope or get something, and suddenly you've got a theory that the universe is expanding or contracting or that it's vomited up by a goat or something like that. It's very hard to find the actual truth. You know that. You've got to do these detailed, careful experiments and careful measurements, and the slightest mistake or error or measure or imperfection or anything completely throws it off. Everything's very fragile and delicate to prove significant results. Everything's fragile and delicate to develop significant software. So things are going to be breaking, and our main task as a programmer is managing this problem. So how we're going to manage it is with skepticism. Whenever we write something, we're not going to assume it's correct, we're going to assume it's wrong. We're going to have methodologies that we follow that mean our code is less likely to have mistakes. That's just systematic programming. We're going to, and designing it properly up front. We're going to have methodologies we follow so that the mistakes in it are easier to spot, and that's called a style guide. It doesn't stop mistakes being in there, but if you follow the style guide, the mistakes are clearer. There's less corners for the mistakes to hide in, so they'll stand out more. And then there's things we do to, once the mistakes get in there and we can't spot them, there's things we can do to tease them out. Because of course, once you've got a mistake in your program and you don't see it, you look over the code once, you know there's a mistake, you read the code and you don't see the mistake. Is there any point in reading over it again? Essentially not, I'd say that. Once you've read through it once and your eye has missed the mistake, your eye will always miss that mistake. Has anyone done the of thing? You know, someone gives you a sentence and asks you to count how many F's are in it? The crazy thing about that, some people get it right, some people get it wrong, but what I find really interesting is if you get it wrong and someone says, actually there are 13 Fs in that sentence, not 10, you can't see them. If you miss them the first time through, no matter how many times you go back over it, you just can't see those missing Fs. Can someone put a link to that up? Because that's quite amazing. So everyone can do it and convince themselves of this. And it's not until someone shows you that you know. Now I gave you the example of the binary search. It had a mistake in it. The person that wrote it didn't believe there was a mistake in it, so they kept hunting and searching and testing and they didn't find the mistake in it. Then I gave them a printout that proved there was a mistake in it, but not saying what it was. They were able to find the mistake very, very quickly. All right. So what we're talking about today is this managing mistakes, how we can find them, how we can correct them, how we can fix them. And the strategy we're adopting in this course is once we've written the code, it complies with the style guide, we're going to pass it through tests. Those tests, just like in science, can never prove it's right, but sometimes if we're lucky, they can prove it's wrong. So if it passes all the tests, we don't go, woohoo, our program's correct. We go, oh, damn, I didn't find the bugs. But if it fails the test, we go, woohoo, I found one of the bugs. And we're really excited. So you understand, we get confidence one way, we can never get confidence the other. All right, so that's the whole story. So now we're going to write some unit tests and show you how to write unit tests. Straight away, let's have a puzzle, a problem that we're going to code up. And the problem's going to be this. When you type a string in a programming language, like when you're actually writing the source code for a program, sometimes you have brackets in that expression. Like you might say, if x is greater than 5, or x equals y3. Oh, what have I done wrong? Is that right? Thank you, double equals. That's the worst error. Because that's one you'd never see. But I'm glad you saw it. Who saw that, by the way? Who saw the single equals versus double equals? Well done. I think that is such a good thing. I'm going to put that in an exam, and I'll even tell you now. One of the exam questions, I've just decided, unless I forget, one of the exam questions will have a pair of a single equals instead of a double equals. And it'll be hidden inside a program completely about something else. And I'll say something like, there's a bug in this program, fix it, or something like that. And you'll be thinking about all this other stuff, and maybe you have to do all this work on the other stuff, and maybe the other stuff is 90% of the question, but all I'll really be looking for is who can actually spot that it's missing one of the equal signs. So we are missing another bracket, and it's a curly bracket on the far right. Okay. It won't compile? Oh no, that's in some programming languages this would compile. Have you ever programmed in stupid? It's a fantastic language. You just have questions with no answers. Actually, it's not stupid, it's called Socrate. The language Socrate is just you ask questions, but you never actually answer them. Okay, so this is a line in a computer program, but another way of viewing it is it's just a string, isn't it? I mean, I could have this as data, I could call this my name, I could enter this into a web form as my name or something crazy like that. This is just a string of letters and symbols. The compiler looks at this string to work out if there's a mistake. You guys, well, being my compiler there, you looked at it and you saw that I was missing one of the brackets. And essentially you were noticing that the brackets weren't balanced. Do you see that? Compilers, when they look at it, have to notice if things are balanced or not. Let's write a program called isBalanced that takes in a string and returns true or false depending on whether the brackets in it are balanced. The type for a string, we've got two options. What are our options? Char star. Yep, or we could an array of characters or a pointer to the first character. And does everyone know how strings are represented? Put up your hand if you know how strings are represented in C. Oh, that's less than half of you. Put up your hand if you do know but just didn't put up your hand because you don't like putting up your hand. Okay. That still leaves about a third of you. So let me just quickly say, in C, if the memory in your computer looked like this, let's just draw it as a single long line. And this is memory location 0, and this is memory location 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 9 bytes in memory. A character takes up a whole byte. A string is a collection of characters, right, organised in a sequence. There's all sorts of ways you could store them. In C, how they store them is like this. It stores the letter. What's the string I'm trying to store? String. Oh, no, that's going to be confusing. Not a string. If. No, pick a string that's clearly a string.
Hello world.
Hello world. Hello world. It's too long. All these constraints on you. This is another exam question. Question 3. Pick a string that's clearly a string that's not too long. Apple. All right. A. A goes in the first cell. What are we storing for A? Is it a string or a character? Character. A, P. P. L, E. Now, you could say this is an array of characters.
What about the /0 at the end?
Oh, yeah, that's a good question. That's a good question. You could say that this is an array of characters. If it's an array of characters, because C is hopeless with arrays, it forgets, as soon as it's created one, essentially, how long it is. Once you give it to someone else, they don't know how long it is. And all security, well, a whole lot of security violations occur because people forget how long strings are and manage to get tricked into reading past the end of a string. So if we were passing a string into someone, into a function, and we were representing it this way, what would we have to also pass in? The length. So we'd have to pass in some metadata as well as the string. One way of dealing with this, and C's a fairly hacky language, is you can mix the metadata in with the actual data, and C chooses to do it that way. So C marks the end of the string using, puts a 0 in. Yeah, the character 0. How do I do a backslash on an angle? That's hard. #0. So the character, literally the character 0. Literally the character with code 0, not the
Number 0.
Yes, now that's confusing because the character 0 actually is what code represents the character 0? 48, is it? You guys are scarily fat. I mean that in a nice way. Yeah, so 0 is 48. So when the computer stores 48, it means this character 0. When it stores 49, presumably it means a character 1. When it stores 100, it means apostrophe. It uses codes to store characters. You know all this from the last course. So the character number 0, which you can't draw anyway because there's no symbol that corresponds to it, but storing the number 0 is how we mark the end of a string. Notice if we're dealing with arrays and we're passing around arrays of characters, you always got to be careful with this terminating 0. Make sure if you're writing a string into an array, you've got to make sure the array is long enough. And make sure if you're reading it, you don't read past the #0. It's slightly annoying that strings can be viewed in two different ways. One is as an array, and an array with a given length, and one is an array terminated by something. You can. I mean, it's just ripe for errors, isn't it? But we don't want to diverge down there at the moment. Let's just suppose that's how we're representing our string. That's how we're storing the string. How do we represent the string in C? How does C know the string apple? That's how we tell it it's a string. But if I had a variable in memory called apple, let me draw my memory up here. I don't want to rub that out. Here's my memory. This particular location in memory here is where the current version of C, the executing program, believes the variable the string. What's the string called? We've given a name, word or something. We've declared string word. So the variable word is stored in here. What literally gets stored in here? Do we store A, the first letter? No, we don't. What do we store here? A pointer to the first letter. Now, you can see up there, where did I store the first letter? 0. So I put a 0 here. It's actually rare to actually store things at address 0, but if I had stored apple at address 0, then word would be the number 0, and word is a pointer to a character. Because if you follow that 0, you get to a character, and that's a character A. So a pointer to a character is also another way of representing a string, because once you've got a pointer to the character, how do you find, that's the first letter of the string, how do you find the next one? Increase the pointer by 1 and look at the next memory cell and so on and so on. And you keep toddling along until you see the 0. Okay. So that's how you can represent a string as a char star. It's a pointer to a character. The other way of representing it is just as an array of characters. How does C represent arrays? As pointer to the start of the array. So again, it's a pointer. So it would look exactly the same. So this is why we have these two types that really look interchangeable. If I was to declare it as char fruit, and over here I've said char star word. Well, fruit, suppose the memory address allocated to fruit was down here. The array gets stored here. This is where fruit goes. And C stores arrays, as I'm sure you remember from the first course. C stores an array as a pointer to the start of the array. Where's the start of the array? 0. So it looks the same. When you're passing it into a function, it sort of looks like you're doing the same thing, passing in a char star or passing in an array. Okay, that was a long diversion. So we're writing our isBalanced function, but we're going to adopt our skeptical approach. Did I want to rub that out? Maybe that's a good example to keep there. You're too smart for me. Okay, let's... I'm now about to write the function, and I'm actually going to do it on the computer. But let's just think about the big picture before we dive in. Because when I write this function, what do we know is going to happen? It'll be wrong. There won't be bugs, there'll be errors. Embarrassing, shameful errors. It'll be completely and utterly wrong. So what approach am I going to adopt so that this doesn't cause us a serious problem? I'm going to write some tests. Yeah, I'm going to work out tests for it. What are some test cases? So we come up with our test cases first. What are some test cases to check if isBalanced works? An empty string. Should that be balanced?
Yes.
Okay. That's test case number 1. That's a good one. I like that. Because that's stressing the program out. If it's expecting a string, if it's expecting it's going to be at least one long, if it makes that assumption without anyone noticing, that'll cause it to crash. And it's a good test case. Testing a boundary condition. Give me another test case. Oh, no, you've already done one. You. Yep. A test case. Oh, you weren't paying attention. If I had implemented isBalanced and you didn't believe it was right and you wanted to pump something into it to make sure it was wrong, what would you pump in?
A wrong case.
Yeah, what's an example?
Like 3 brackets.
Okay, you'd pump in something like maybe... How about that? Yeah, something that's supposed to be wrong. That's a good test case. Any more test cases people can think of? What's that?
The right one. The balanced one. The balance.
I'll give a balanced example. Yeah, give me one. Open, close, open, close. You're just doing round brackets. How many brackets have we got available to us? Yeah, let's stick some more ones in. How about opening a squiggly one here and then closing the squiggly one here? Yeah, notice in this example here, this wouldn't have been balanced if I'd written it like this. Yeah, that's not balanced. This one has to come before there. So, because the adversary does that. Well, you're not looking. Okay, all right, so we've got this. This one is balanced, yes. Okay, enough writing on the blackboard. You get the idea. We're going to actually write it live. Yes?
2 to the 32 brackets one way.
A ridiculous number of brackets going one way. 2 to the 32. 2 to the 32 brackets would actually overflow, wouldn't it? Overflow my computer's memory, wouldn't it? Yeah, it'll overflow. Yeah, we're in just serious trouble here. So I like that. We always think of the trivial boundary case, but the other boundary case is when things overflow or get too big. And we'd have to look at the spec for the function for how long the strings are supposed to be. Normally we leave that vague and open in C, and C's a bit vague about the amount of bits it allocates to each type. But yeah, so we'd have to have some guarantee for the maximum length this would work. So if they didn't give a guarantee for the maximum length, pumping in the longest thing you can pump in is a brilliant idea. That's fantastic. I like that. Stress testing. Okay, so now we've got some tests. We're going to write our function. We've planned the tests. This is the development cycle I suggest you follow that's going to lead to us finding our errors as quickly as possible. We plan the tests. We write the general shape of our function. We write the tests. We don't implement the function. We run our unimplemented function on the tests and it fails, hopefully. If an unimplemented function, just one that just returns automatically or always returns false or something, if that passes all the tests, then we're in trouble. We haven't got very good tests, or it wasn't a very interesting function. Then we run our tests on our unimplemented function. We check it fails. We implement the function. We run the tests again. We check it passes. That's going to be our general approach. And our tests are going to be unit tests using the sort of style we use in the course. So let's actually write them now. So the first thing we have to write is the general infrastructure, the file names and prototypes and things like that. We don't have to worry about. Notice we don't implement isBalance till the very end. We do all our housework first. Oh, I haven't shown you how. I showed you briefly at the end of last lecture how we do unit tests in the course. Let me show you from the prac exam here. This is one of the questions from the prac exam. Oh, let me just make that fit on. Okay, here's how we had the three files. You had to write a function called median that, given an array and a length, returned the median element. Median means if the numbers in the array were sorted into order, it would be the middle element. So you had to write that, and you put that in a function called median. You put that in a file called median.c. The prototype for that was in a file called median.h, which told you the type of the function. And then we created another file called testmedian.c that tested it and ran tests against it. Here's how testmedian.c works. Notice testmedian.c starts off with our main function. It has the main function. There's no main function in the median file. It just calls one subtest function in this case called testmedian, and then it returns success. And testmedian does a little bit of work setting stuff up. Then it prints out, I'm about to do this test, blah, blah, blah. Then it does the test with an assert. Now what happens if the assert succeeds? It continues silently, prints nothing and just continues. If the test fails, it stops and prints out a message. Why are you? Why what? Why is there a comma there?
No, because you usually get a semicolon.
Who? Yeah.
Copy pasted the commas in.
No.
Try to compile. What happened?
I just ran this. This is crazy. All right, let's have a look. Oh, it is valid C. Oh, yes, it is valid. The comma operator. Yes, yes. C actually has a comma operator that lets you join two statements together. It still executes both the statements. Well, there. Thank you, C. The error distance between what we won and what we wasn't was one little dot. Okay, there we go. Oh, well, now, the comma operator, which we won't ever use in this course, runs both expressions. Now, someone tell me, what's the details? Comma operator evaluates both statements. The order is not specified, so it's not lazy, it's a strict evaluation. In either, it evaluates both of them in any order, and then the value of the whole expression is what?
No, it does separate things, and it just allows the compiler to pipeline. So.
But the important thing is, I think the result of the expression, the result of the command, is the last thing in the comma, I think. Is that right?
I can do something like I equals 0 and j equals 0.
Yeah.
Comma j equals 0.
Yes. The problem in C, which is something we've sidestepped completely in our first course, is even statements in C have values. Crazy. So it's just there for laziness. We take it out. It's there to let you compact a lot into one line. So we take it out. So it still would have evaluated both those things, but if, as you're saying, it would have evaluated them in either order, it might have told you the test passed before failing the test. Which would have been very funny. So that's just missing a dot. Yeah, that's another really funny thing for me to put in the final exam. Yeah, to prove you're in the lecture. That's right. Yeah, and for whoever's taking the notes, just say, don't forget, ... Those 3 missing dots. And we'll know what it means, and those people who didn't turn up. That stuff. Okay, so notice here's what we do. We print out, we're about to do the test, we do the test, and then we print out that we pass the test. This actually still isn't particularly brilliant code I've written here, but before we look at how I can improve it, why are we printing out first that we're about to do the test? So we know what test we're up to. So when it fails, we get some sort of meaningful output. And why do we print that it passed the test? So we know it's down to the next one, but also it just makes us happy. It's just one of those little things you can do in life to make you happy. So those little paths that pop up all the time, they just give you great joy. What's that? If you pass the test case, no, you should be happy. I know part of you is sad because you think you haven't found the bug, but another part of you is happy, and I think we should concentrate on the happy part. Yeah, uber happy. So here's what I should have done though. I should have put a new line at the end of every line. Why is that? C, until it sees a new line, sometimes it buffers the output and doesn't print it to the screen. So I guess it's conceivable it could have thought it printed, I'm about to do this test, but really it's buffered it somewhere, and then crashed and not printed anything. So that message, I'm about to do this test, would be sitting in a buffer, and then you'd be very confused, because it would say, about to do this test, passed, about to do this test, passed, crash! And you go, but it's not doing a test. So that would have been confusing. So it's always good, whenever you think possibly the world's about to end and things are about to crash, make sure you've printed everything out before that time, so you get to see what's going on. So make sure you put /nz. Okay, but here's the general approach. Hang on a sec. The general approach, do you see it? Print out what you're about to do the test, print out that you passed. Why am I labouring this point? Because very, very soon, you won't be writing tests for your programs anymore. Within a few weeks in this course, you'll be writing tests for your program. And you'll be writing tests for your program. And when you fail someone else's test, there's nothing more annoying to get told, oh, your program failed, and you look at the log and it says, about to do test 7, failed. Because you think, I have no idea what's wrong with my program. So a really helpful thing to print out just before you do the unit test is print out enough information to let us know exactly what the test is, so the poor person doesn't have to go through the source file looking at your test to work out what's going on. Next week, you've all handed in binary sorts, or they'll be handed in binary searches. They'll be handed in by Monday, won't they? Binary searches and test cases. Next week in the labs, we run everyone's test case against everyone's binary search, and you get all the errors that other people throw out for yours. So please make sure when you write your test cases that you put helpful error messages there. Otherwise it'll just annoy people. Don't say things like sucked in, or you smell, or I hope you fail the next test. Okay, write helpful error messages. What goes around comes around. Okay, so that's all our test is. Notice because we have this sort of mindless approach, it's an exception-based approach we call it, that we just assert that the thing works, and then we assert the next thing, and we assert the next thing. All our functions, testing functions, just return. There's no value to return. The fact that they're able to return means we've passed all the tests. So it doesn't return any value or anything to say everything worked. It just literally at the end just returns. Yep, so the function's a void function. At the end we print all tests passed. By the way, in the major project, when we're running everyone's code against everyone else's tests, whenever you fail someone's test, we print out the log so you can see what's going on. Because the log can be quite long if they've got 1 million tests in that file, and they give you very good descriptions about what each test is going to do. You don't necessarily want to read the whole file, you just want to read the bit for the tests that you failed. So what we do is we strip out the whole log. Well, you can see the whole log, but if you want the abbreviated log, we strip out the whole log up until the last passed message. So do make sure you always print out this passed exclamation mark when they've passed a test, and that means if they fail the next test, everything above there gets stripped out and they only get to see the log for the thing that failed, and that just helps everyone too. So please always do print passed and put an exclamation mark at the end, and then ba-bum, we're in. Okay, so that's our testing strategy. Let's actually write it for now for our balanced. Oh no, I'll just shut you down. Go away. Shall I save you? Yes, please. And now here's one I prepared earlier, but only slightly. Where are we? Okay, let's look at brackets. Here's our function, balanced. Oh, I called it is balanced over there, but it's balanced. It takes in a string, and we've happened to have represented a string. We happen to denote it using array notation. So this is the function, returns true or false depending on whether the string's balanced or not. Woohoo! So that part's done for us. Now what about the implementation? Is that done for us? Let's see, what have I implemented? Oh yes, I have. I've implemented it already. And what about test brackets? All right, we haven't written any tests. Notice the unit test file is the one that's got the main function in it. So let's write a test together. What am I going to say first of all? I'm going to say test, what's it called? Test brackets. Test balanced. Okay, I guess, because I'm testing the balance function. I've just created a new function. Oh, I'm returning 0. That's not good, is it? If I say exit success, now I've got a hash include stdlib.h. Not balanced. Now test balanced, I better give it a prototype for test balance. What is the prototype for test balance? Void is not going to return anything. It's called test balanced. What's it taking in as arguments? Nothing. To say nothing, we say void. That means no arguments going in, no arguments coming out. Bit like my attempt to, okay. Yeah, if you don't put the void in here, it turns off parameter type checking, so put the void in there. If you take the void out here, then it assumes it returns an int. Thank you, see? But you guys explicitly, even when you're returning an int, please do say the return type.
Oh, I thought that if you take the void out at the beginning, it won't compile.
Yeah, well, it'll compile, it'll just think it's an int. So as long as you use it everywhere and it does return an int, it won't grumble about it. But that's...
If you forget to put the void there, if you accidentally call it with an int, can it like show something?
Shh. Can we just have quiet? Are you talking about this void?
No, one in the bracket.
If you leave this void out, it just turns off parameter type checking. And yeah, you can pass stuff into it still. Experiment is my answer. Whenever you have a question about, oh, if I do that, I mean there's...
See, the last time I took the void out of the beginning, it didn't
Yes.
compile, so...
If you take the void out of the beginning, it will compile. Yeah? But it will assume it's returning an int. But don't believe me, and let's not talk about it because this is a really slow way of doing it. Try it out. Yeah. Do some experiments. Yeah. As success means the main function always returns an int, and that int is a sum. Let's think, who calls the main function? We never call main. Who calls it? The operating system calls it. When it starts our program up, the first thing it does is call main. So when main returns a value, who's it returning it to? The operating system. And it's telling the operating system, woohoo, I finished okay, everything was all right. Well, what's the point? Your operating system can test this exit value to work out if the program worked or not. In both in DOS and Unix, you can test for this value. So you can say, I don't know, open a file, if you've got a program to open a file and you can test if that succeeded or not. Yeah. Yeah, in a batch file you can test the exit result. I can't remember how you do it in Windows, but there's a variable that's set, that's the exit value.
Test the testing program.
I like it. What's your name? Tom said, well, actually, why don't you say it really loudly? You don't want to say it loudly? Shh. Say it at the same volume and everyone be extra quiet.
I asked, how do you test the testing program?
How do you test the testing program? Because, of course, where are your errors going to lie now? In the testing program. Yeah. This is like this thing, who will test the tester? There's a Latin quote for that. Ips testodius. Ipsos custodius. Shh. You cannot test the testing program. It's insane. So what you've got to try and do is your testing program can't do anything fancy. Don't have any corners where bugs can lie. If your testing program uses helper functions, then you have to write unit tests for those helper functions. Don't ever have a big elaborate test that does a lot of computation. If the complexity of the testing function is in the same order of magnitude as the complexity of the things you're testing, the whole thing's completely pointless. Well, not completely pointless, but you've lost confidence. So yeah, make your tests simple. And you'll notice the test we had for the other one I was showing you before was simply, I gave an array of 5 characters. You can check it with your eye. You pass it in, you say what the median value is, you can check that with your eye. So somehow it was simple enough that my brain could just accept that it was right. And that's sort of how maths works too. You have some elaborate claim, you reduce it to smaller claims and simpler claims until eventually you get to axioms. You can't reduce them anymore, but the whole idea of picking good axioms is they're things that should be sort of self-evidently true, and your brain can encompass the whole thing. So yeah, I pretty much accept that that's the case. Yeah, I mean, this is right. You're being good, skeptical. I like it. It's very good. Okay, so we're writing our test, so test balance is void, void, so everything's looking good. Let me make this the right size. Have I been talking for a very long time? And I said we're going to do coding all the time. We've hardly done any coding. What time is it now? It's nearly 5 o'clock. Okay, we haven't played any music, so I'm just going to play a little bit of music. What's that? Coding music? This is coding music. Oh, no, not that code. No, listen. Shh, 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 shh. Shh, shh, shh. Excellent, excellent. Piano accordion music. There's nothing like some good folk music to get you doing that. So that's very good. Does everyone know that song, by the way? What song is that? That's Where Do You Go To My Lovely. Where do you go to, my lovely? Yeah, it's very, very nice. It's where do you ... Yes.
Like Marlene and Dietrich, and you dance like Zizi Jeanmaire. Your clothes are made by Balmain, and there's diamonds and pearls in your hair. Yes, there are. You live in a fancy apartment.
Just hang on a sec.
Off the boulevard Saint-Michel, where you keep your Rolling Stones records, and a friend of Sacha Distel, yes you do. But where do you go to, my lovely, when you're alone in the open?
Hang on a sec.
Tell me the thoughts that surround you. I want to look inside your head, yes I do.
Oh, fantastic song. Now, that song turns out to be very, very important, so I hope you were writing the words down. Who was taking the notes today? If you weren't writing them down, I actually have put them on the web for you. The URL is Google, where do you go to my lovely lyrics.com. Okay, now, so we're actually going to, before we stop, I actually want to write some code. So let's actually write this damn code. Where am I going to put, where do you go to, my lovely? Where's it going to go to? Off to the side. That's where it goes. Okay. Let's write our function now. We've got test balanced. Our simple unit test is simply going to be, well, you tell me. Let's just do one test. How are we going to do it? I guess I'll assert something. Is that the first thing I'm going to do? What am I going to do? I'm going to print out what I'm about to do. I'm going to say printf testing if dun 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 dun. It's like that song, Isaac and Fuzz. Testing if that is balanced, say, /n, so we don't lose the message if it's not. And then I'm going to assert, what am I going to assert? Is balanced, which I think I just call balanced in this life. Balanced, dun 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 dun. There we go. See, completely not error prone, isn't it? Your eyes can scan that in a second. And then what are we going to print? Printf. All passed. No, sorry. Passed, thank you.
Capital P.
Was it a capital P? No, I don't think it was. And at the end of doing all our tests, what do we say? Because we'll have several tests here. Printf. All passed. Woohoo! All right, we're done. All right, let's run it. Let's see if it works. Because I did actually write a brackets.c before. I mean brackets.c before. Have I loaded it in? Oh no, it's not going to... I missed a bracket somewhere? What? What? You're distracting me. Okay, let's stop. We'll find it. Mr. Compiler will help us. Now, yeah, it doesn't know where the function balanced comes from. That's in the file brackets.h, but I haven't included that. So I better go hash include brackets.h. What else is missing? What other hash includes do I have to put in? I haven't put in standard IO, have I? Yet I'm printfing. Yep. Yeah, exit success is in standard lib. And assert.h. Thank you very much. Without assert.h, we won't be able to do asserts. Whew. Gee, there's more sort of preamble than there is amble. Let's have a look now. Go. Oh, it ran. Let's look at the output. Our console. Stop that pausing. Look at that. Testing if that is balanced. It must have been. It passed. All passed. Aha! Fantastic. So we rejoice. Thank you. So what do we know now? What does that tell us? It works on that case. It tells us we haven't found the bug. But we're very happy. Now, every time you get all passed, you're happy and you rejoice. So let's actually implement this thing now. No, we're not going to implement the thing now. Let's implement it in a second. Let's first of all talk about something else. Oh, shall I take a break? Let's take a little break to the beautiful music of Where Do You Go To, My Lovely?
You talk like Marlene Dietrich, and you dance like Zizi Jeanmaire. Your clothes are all made by Balmain, and there's diamonds and pearls in your hair. Yes, there are. You live in a fancy apartment off the boulevard Saint-Michel, where you keep your Rolling Stones records and a friend of Sacha Distel. Yes, you do. You go to the embassy parties where you talk in Russian and Greek, and the young men who move in your circle, they hang on every word you speak. Yes, they do. But where do you go to, my lovely, when you're alone in your bed? Tell me the thoughts that surround you. I want to look inside your head. Yes, I do. I've seen all your qualifications you got from the Sorbonne, and the painting you stole from Picasso. Your loveliness goes on and on. Yes, it does. When you go on your summer vacation, you go to Juan-le-Pin with your carefully designed topless swimsuit. You get an even suntan on your back and on your legs, and when the snow falls, you're found in Samoritz with the others of the jet set, and you sip your Napoleon brandy, but you never get your lips wet. No, you don't. But where do you go to, my lovely, when you're alone in your bed? Won't you tell me the thoughts that surround you? I want to look inside your head. Yes, I do.